To illustrate calculation of swing limits, we will now study the swing limits of common source amplifier with a different biasing arrangement, that is using drain feedback. Okay. Now, the common source amplifier using drain feedback looks like this. We have the input source, which is AC coupled to the gate of the transistor, and there is a current source which biases the drain, and there is feedback to the gate using a very large resistor RG, and of course there is a load. And for illustration, let me assume that the supply voltage is 15 volts. This C1, C2, RG are all very large. Very large meaning when they are very large, you can make certain approximations. Essentially, that RG almost behaves like an open circuit and C1 and C2 behave like short circuits. Okay. Now, if this is 100 kilo ohms and let's say RG is some 20 mega ohms or so, this constraint is easily satisfied. C1 and C2 I won't evaluate, but we have done it many times and you know how to do that. Okay. And let me say that the load resistance is 40 kilo ohms. Now, just to make it more interesting and also to illustrate a point which will come later, I'll assume that this current source here, this 200 microamperes, is replaced by a resistor. I had mentioned earlier that many times you don't want to use current sources, but you use resistors for biasing, especially in case of discrete circuits. So let's say we do that. What resistor do you substitute it with? You know what current source this is, it is 200 microamperes, and you know what voltage drop there is across it, because for a drain current of 200 microamperes, the gate source voltage of the transistor is 3 volts. And because no current flows through RG for DC, the drain source voltage is also 3 volts. So this point here is at 3 volts and this is at the supply voltage of 15 volts. So there is 12 volts across 200 microamperes. Okay. 200 microamperes with 12 volts across it is replaced by a resistor which is 12 volts by 0.2 milliamperes or 60 kilo ohms. Okay. So I'll do that. So 60 kilo ohms. Okay. Now let's analyze the swing limits of this. Now the procedure to analyze swing limits is always the same. You first compute the total quantities, total VGS, VDS and ID. To calculate the total, you sum the operating point plus the increment, and the increment of course comes from small signal linear analysis, and that's where the approximation comes in. Okay, so that is the approximate part, but that's okay. And then you apply the conditions for the transistor going into triode region, or to prevent it from going into triode region and to prevent it from going into cutoff. And for cutoff, we always use the criterion based on drain current as opposed to the gate source voltage. Now, while evaluating the condition for the transistor going into triode region, you can either use the total VDS in terms of the total VGS, or sometimes you can just use the drain and gate voltages. This also has been discussed before, but of course you have to use the total voltages, not just the quiescent voltage or the incremental voltage. Okay. So one of these is convenient in some cases, the other one is convenient in other cases. So let's carry that out for this particular circuit. So by now you should be quite fluent with calculating the operating point, writing down the small signal picture and doing those calculations on the small signal incremental circuits. So I will go quickly through those parts of it and spend time on the actual calculation of the swing limits. And also, because we've been using the same transistor parameters, In fact, I didn't even mention that. As usual, muon Cox is 100 microampere per volt square, and the threshold voltage is 1 volt, and W by L is 1. So that's why for a 200 microamperes of current, I have a gate source voltage of 3 volts. Okay. For 200 microamperes of current, I have a gate source voltage of 3 volts. This is 60 kilo ohms, and the load is 40 kilo ohms, and these are large AC coupling capacitors. Okay. So the operating point is that VGS0 is 3 volts and ID0 is 200 microamperes. Okay, and VDS0, that is the quiescent VDS, is also 3 volts because no current flows through this. Okay. Now coming to the signal picture, so let's say RS is 100 kilo ohms. Again, it doesn't matter. This is VI 100 kilo ohms, and I have the transistor, gate, drain, and source. Okay. I have the 60 kilo ohm resistor I use for biasing, and a 40 kilo ohm load resistor. This is VGS, and this is GM times VGS. You also know, having done these calculations many times before, that GM at this operating point is 200 micro Siemens. Okay. There is the resistor RG, but we have chosen its value to be so large that it can be neglected. Okay. You can refer to the lesson on common source amplifier using drain feedback to see the constraint on RG. I have chosen it to be so large that it is negligible, so I am not even going to include it in any of the calculations. Okay, it's as good as it being an open circuit. And this 20 mega ohm is some value I put down. You can even imagine a much higher value like 50 mega ohm or whatever. Okay. Now the parallel combination of these two, 60 and 40 kilo ohms, is 24 kilo ohms. Okay. So from this we can see that the incremental gate source voltage is VI itself, because no current flows into the gate and RG is so large that no current flows into it either. So I assume that all of VI appears here just like it would in a common source amplifier. So VI appears there. The incremental drain source voltage is nothing but minus GM RD parallel RL times the input voltage. So this is minus GM RD parallel RL times VI, and in this particular case it is minus 4.8 times VI. Okay. This product is 4.8, and the drain current, again assuming no current through RG, all of it flows here, and that is equal to GM times VI. Okay. So the incremental drain current is GM times VI, or 200 microsiemens times VI. Okay. So let me put those things down. The incremental VGS equals VI, ID equals 200 microsiemens times VI, and VDS, which is here between these two, it's nothing but the output voltage. It is minus 4.8 times VI. Okay. With VI equal to 0, here you get the operating point conditions, and from this picture you get the incremental quantities. Okay. So you add the operating point quantity to the corresponding incremental quantity. Okay. So the total quantities will be VGS total is the operating point part plus VI, VDS total is the operating point part minus 4.8 Vi, that's the incremental part of it, and ID total is 200 microamperes plus 200 microsiemens times Vi. Now the cutoff due to triode region, or to prevent it from going into triode region, prevent the transistor M1 from going into triode region, I'll call this M1. VDS total has to be greater than VGS total minus VT. And the condition is exactly the same as before. Okay, we are talking about a common source amplifier. So what do we have? VDS total is VDS 0 minus GM RD parallel RL times Vi, and this should be greater than VGS total, that is VGS 0 plus Vi minus VT. So as usual, Vi has to be less than VDS 0 minus VGS 0. This is the quiescent drain gate voltage, how far the drain is above the gate at the operating point, plus VT. That's because the drain can go below the gate by 1 VT, but not more than that, divided by 1 plus GM RD parallel RL. Okay, the gate is going up, drain is coming down, so you have this in the denominator. And in this particular circuit, VDS 0 and VGS 0 are exactly the same. In fact, that's one of the disadvantages of this configuration using drain feedback, because the quiescent drain voltage and gate voltage will be exactly the same as each other. So that means that there is not a lot of room for the gate voltage to rise and the drain voltage to fall before it enters triode region. Okay. If you had a different kind of biasing, or somehow modify this biasing so that this voltage is far above the gate voltage in quiescent condition, then the swing limit will be higher, because the gate voltage can rise by a large amount and drain voltage fall by a large amount before the transistor enters triode region. So anyway, in this case, VDS 0 equals VGS 0 equals 3 volts and VT is 1 volt. So it turns out that Vi has to be less than 1 volt divided by this number is 1 plus 4.8 or 5.8, which works out to 0.17 volts. Okay. So Vi has to be below 0.17 volts. And if you evaluate the cutoff limit, to prevent cutoff of M1, ID has to be greater than 0. As I mentioned in the previous lesson, another possible limit is to say VGS total has to be greater than VT, but we don't use this limit, we use this one. Okay, which means that ID 0 plus GM Vi has to be greater than 0, or Vi has to be greater than minus ID 0 by GM, and in our case it is minus 200 microamperes by 200 microsiemens, which is minus 1 volt. Okay, so the limits for Vi are that Vi should be smaller than 0.7 volts, and this limit is to prevent it from going into triode region, and it has to be greater than minus 1 volt, and this limit is to prevent it from cutting off. Okay, so Vi, if I plot Vi, the limits are somewhere here. The upper limit is 0.17 volts and the lower limit is minus 1 volt. Okay, so these are the limits, and as far as we are concerned, according to our crude approximation, within these limits it behaves like a linear amplifier. We know that as the input amplitude increases, the distortion, the nonlinear product slowly increase because the small signal or incremental analysis with linear approximation breaks down. But to get an estimate of how much signal we can apply, we say that if it is within these swing limits, then the amplifier behaves linearly, and otherwise it doesn't. Okay. So you could have any signal which is within these limits and it will behave linearly, but let's say if it goes outside that, then in these parts it won't faithfully reproduce the input signal. Okay, so clearly you should avoid this. Now if your signal happens to be sinusoidal, then obviously it has to be symmetrical around 0. So then the smaller of these two limits, 0.17 and 1, will decide the amplitude. So if you have a sinusoid, the only way to fit a sinusoid here is to have an amplitude that is either 0.17 volts or below. Okay. So if you are interested in having symmetrical limits, which is mostly the case, you should adjust your swing limits so that you do have symmetry. Okay. So far all our analysis has focused on the small signal picture, but the swing limits do very much depend on the operating point. Okay. So we had many options, right? Different kinds of biasing and different values of quiescent VDS, VGS, etc. that could be chosen. So far we would choose them arbitrarily, but now we know their role. They play a role in setting the swing limits. So we have to choose the correct biasing technique, the convenient biasing circuit, as well as the correct quiescent parameters to get the optimum swing limit. Okay. So let me also write down that maximum sine wave that can be fed in has an amplitude of 0.17 volts. Okay. Now this cutoff limit is one more interesting thing here to see exactly what happens at cutoff. We have expressed the limits in terms of the input voltage Vi. Vi should be between 0.7 volts and -1 volts. Sometimes you want to know what is the output signal that can be produced so that it's a faithful copy of the input, and that's very easy to calculate because we still use the relationship between input and output based on the small signal incremental picture. In our case, V0 is minus 4.8 times Vi. So from this we can write that V0 should be between 4.8 volts, which is due to this one. It is -1 times minus 4.8, so that limit appears here. So this is due to cutoff. Okay, and on the other side we have 0.7 times minus 4.8, which is about minus 0.83 volts. Okay, so if you evaluate the limits in terms of the outputs, this is what you will get. Okay, so this is due to cutoff and this or this is due to triode. Okay.